Hello, friends. Grab your coffee, grab your cookie, and maybe leave your sneakers at the door, because today we are talking about rubber dust. Yes, the dust that somehow smells like tires, sticks to everything, and behaves like it still remembers it used to be flexible. My name is Michael Klepik, and I have spent 15 years building systems for grinding lines, tire recycling plants, rubber molding operations, and polymer mixing rooms. Today I will break down what rubber dust is, how it behaves, and how we safely remove it from the air. What rubber dust really is, technical description. Rubber dust is a mix of fine particles released when rubber is cut, ground, milled, shredded, buffed, or recycled. It usually contains natural rubber, synthetic rubber, carbon black, fillers, oils, sulfur compounds, and trace additives. Typical properties. First, particle size ranges from 1 micron to about 500 microns, with the most airborne fraction from 1 to 10 microns. Second, bulk density usually ranges from 200 to 350 kilograms per cubic meter, depending on carbon black content. Third, dust clouds can reach concentrations from 500 to 20,000 milligrams per cubic meter at shredders and grinders. Fourth, rubber particles contain oils and additives, making them sticky and difficult to filter. Fifth, carbon black content increases static electricity and makes the dust electrically conductive. Rubber dust is not a simple dry powder. It is a complex, oily, elastic material. Where rubber dust appears in industry, rubber dust is produced across many processes. The most common sources include, first, tire recycling operations that shred rubber into granules and powder. Second, buffing and grinding lines used to resurface tires. Third, rubber molding plants producing gaskets, seals, hoses, and belts. Fourth, rubber sheet cutting and trimming operations. Fifth, polymer mixing rooms where rubber and fillers are blended. Sixth, conveyor systems transferring shredded rubber. Wherever rubber moves, friction and cutting create airborne particles and vapors. Why rubber dust is dangerous? Rubber dust introduces multiple hazards. First, the smallest particles enter the lungs and can cause chronic respiratory irritation. Second, carbon black increases toxicity and can stain surfaces and lungs. Third, rubber contains oils that can release volatile organic compounds when heated. Fourth, dust buildup around motors, belts, and bearings can ignite under the wrong conditions. Fifth, some rubber blends are combustible, especially when dried and pulverized. In recycling operations, the combination of dust, friction, and heat makes proper air handling essential. Technical behavior of rubber dust in airflow. Rubber dust has several unique physical behaviors. First, it clings to surfaces because of oils and electrostatic effects. Second, it forms clumps when compressed or exposed to humidity. Third, it has low mass compared to metal dust, so it stays airborne longer. Fourth, it accumulates inside ducts if airflow is too slow. Fifth, it absorbs odors and can make a facility smell permanently like a tire warehouse. For stable transport, I designed duct velocities from 4,000 to 5,000 feet per minute. What filtration equipment works best? Because rubber dust behaves unpredictably, equipment selection must match the dust properties. For fine airborne rubber dust, I often use a faux EHN cartridge collector. First, it captures small airborne fractions efficiently. Second, it handles carbon black particles well. Third, it supports strong pulse cleaning for heavy, sticky, or mixed rubber dust. When the dust is oily, fibrous, or sticky, I use a Baghouse Blizzard. First, it tolerates irregular, sticky particles. Second, it keeps airflow stable under heavy loading. Third, it is resilient and easy to clean. When rubber dust is combustible, I add, first, explosion vents. Second, anti-static filter media. Third, grounding and bonding across the system. Fourth, isolation valves on ductwork. Fifth, optional spark detection for shredders. Safety always comes first. Odor and VOC considerations. Rubber contains oils and chemicals that release vapors at high temperatures. Typical emissions may include, first, hydrocarbons. Second, sulfur compounds. Third, plasticizers and processing oils. Fourth, traces of styrene or betadine in specific rubber blends. If odor control is required, I add an adsorption stage using activated carbon after the dust collector. The most common mistakes I see with rubber dust. Across rubber facilities, I see the same issues repeated. First, using duct velocities that are too low, causing rubber buildup. Second, underestimating the stickiness and oil content of dust. Third, not grounding ducts despite high static potential. Fourth, using filter media that clogs quickly with oily dust. Fifth, mixing rubber dust with metal dust, a significant hazard. Sixth, ignoring VOC emissions from hot rubber. These mistakes reduce safety and efficiency. What I always do on rubber dust projects. My standard approach includes, first, identifying dust composition, including carbon black content and oil fraction. Second, designing airflow specifically for lightweight but sticky particles. Third, using enclosed hoods around grinders and shredders. Fourth, selecting filter media resistant to oils and clumping. Fifth, adding explosion protection if dust is combustible. Sixth, installing carbon filters if odor control is required. Seventh, ensuring all ductwork is grounded to control static. These steps create a safe and reliable system. Rubber dust may come from old tires, molding lines, or trimming operations, but it behaves like nothing else. It is oily, elastic, full of carbon black, sometimes combustible, and always challenging to control. With the right airflow, the proper filter, and good engineering, rubber dust can be handled safely and effectively. I am Michael Klepik. Protect your lungs, protect your equipment, and remember, rubber dust belongs in the filter, not stuck to your clothes for the next 3 days. See you in the next video.